Okay, hello everyone. How are you doing? We already had some thumbs up earlier um, in Gathertown, but give me a thumbs up if you can hear me now, so I make sure that um, all of the audio is working for you. Excellent. So we're starting today with chapter 8, and chapter 8 is on potential energy and conservation of energy. Both of those are, of course, very fundamental topics in physics. A lot of what we do in physics is based on conservation of energy and on calculations with conservation of energy. And one of the things we introduced for that is potential energy. So um, let's start with a sort of a verbal definition of potential energy. It is the energy of an object by virtue of its position. In those cases when the forces that work on that object are independent, do work that is independent of the path. So remember that there were two types of forces. There were conservative forces and non-conservative forces. The conservative forces were those where if you do work, you calculate the work, it turns out it only depends on the initial and final position or initial and final state of the system. And then there were other forces, the non-conservative forces, that did not have that property. Potential energy is only going to be defined for the forces that where the work is independent of the path. So that includes gravitational force, it includes spring forces. What does it not include? It doesn't include friction, drag, and other dissipative forces. Um, the other definition of potential energy, and we're going to come to that, is that it is the ability of the system to do work. We'll see that if or the ability of a system with a force to do work. So we'll see that if a system is in a higher state of potential energy, if it has a higher potential energy, it will have the force will be able to do work on that system, and through doing work increase the kinetic energy. So let's look at an example, which is this sort of kicking a football. So we have a kicker here who does work on the ball and gives the ball kinetic energy. Right after the ball has gotten that kinetic energy, it starts to move upwards through the air. I was going to say through the gravitational field, but let's not introduce gravitational fields here just yet. So it's moving upwards, and what happens is the kinetic energy decreases, and as the kinetic energy decreases, the potential energy increases. Why does the potential energy increase? Because the work that the gravitational force is doing as this ball is going up in height, in y, that work is negative. So let's look at that as an example here. So let's call this kicking a football. So I guess this is technically step 2, right? 2, the ball ascends. So the work by gravity is, as we calculated last time, is minus mg times delta y. And so in this case, delta y is positive. Delta, forgot my y here. Actually, we should probably put that right here. The ball ascends, so delta y is positive. So this will be negative. So work by gravity is negative, which means if the work by gravity is negative, then the kinetic energy decreases because W is minus the change in kinetic energy. And if kinetic energy decreases, we'll call this a gain or an increase in potential energy. And really the arrow here should probably go closer to coming from the work by gravity is negative, therefore there will be an increase in potential energy. So that's what happens when the ball ascends, right? So we have work by gravity is negative. That causes an increase in potential energy. And we'll introduce this mathematically in a second here, as I'm sure you expected. At the highest point, kinetic energy is at a minimum, especially vertical kinetic energy is 0. There's still going to be some horizontal kinetic energy. Potential energy is at a maximum because we've been, while going up, the work is negative, negative, negative. The potential energy increases, increases, increases. So we're at the highest point in potential energy, lowest point in kinetic energy. Now the ball descends. When the ball descends, the opposite is of course true. If the ball descends, delta y will be negative. The work is minus mg delta y will now be positive. Positive work by gravity. So this is gravity is doing work. Gravity is doing work. The kinetic energy increases because W is minus delta K. So kinetic energy sorry, what did I write here? W is not equal to minus delta K. W is delta K. Kinetic energy increases. And in this case, we'll have a reduction in the potential energy. And this is really the second part. I wish I could have a picture where the kicker actually kicks down and the ball goes up again. Of course, that's not how it works. But this is really the second part is more illustrative for the definition of potential energy that we use. Since potential energy is the ability of a force or a system to do work. So if we're starting at a high point of potential energy, and the fact that we start at this high point of potential energy at this position at a high value of y, that allows the force of gravity to do work in a positive sense. The gravity does work, and that's possible because of the initial position we started from. So that's how we introduce potential energy. Now, mathematically, you'll see that in my description here, there's a reduction in potential energy when there's positive work done by gravity. There's an increase in potential energy when the work done by gravity is negative. So the potential energy which is defined, which is given the symbol U, will satisfy that delta U is minus the work done. So the change in potential energy is the negative of the work. If the work is positive, then delta U will be negative. If the work is negative, then delta U will be positive. And of course, we can also turn this into UB minus UA if this is the work from A to B, and this is the work from A to B. So if delta U is negative, then UB will be less than UA. If delta U is positive, then UB will be greater than UA. So since so this is actually in a sense similar to the kinetic energy. So we had that the kinetic energy was equal, the change in kinetic energy was equal to the work that's being done. Here we have that change in potential energy is equal to the negative of the work that's being done. One thing you'll of course immediately be able to do is combine this and realize that delta K between A and B, two states, has to be equal to minus, I should have left myself some more space here, should be equal to minus delta U AB, and we'll come back to that. So we're talking here about gravitational energy and gravitational potential energy and the force of gravity. As one example, we'll immediately transition to the spring, which is another example where we can use potential energy. So this is more generally valid than just for gravitational forces. It is just an example here to introduce the concept of potential energy. So we can see that we have, in both cases here, the work is equal to the change in some quantity, the change in kinetic energy. It's equal to the negative of the change in potential energy. Now, with kinetic energy, we introduced kinetic energy not through the fact that there's a change and that this is how we got to kinetic energy. For kinetic energy, we actually introduced this as the kinetic energy is 1/2 mv squared. So we have an absolute value. We know what a kinetic energy of 0 means. Kinetic energy of 0 means that the velocity will have to be equal to 0 so that the speed is 0, so the kinetic energy is 0. We don't have that kind of definition in the case of potential energy. So the only thing we know is, the only thing we can relate to quantities like the work is the difference in potential energy. The only thing that shows up is potential differences. Potential energy differences. You'll hear me say potential when I mean potential energy, and those of you who are in electrical engineering or who are thinking of that direction, they'll come back to see exactly what the connection is between potential and potential energy. And if you continue on in physics, you'll see that as well, of course, in electricity and magnetism. There's a very close connection, but I shouldn't mix them up because there's a crucial difference as well. So we only talk here, or we can only connect quantities that are related to forces to potential energy differences. So there's, if we want to assign absolute values, we have to introduce a choice, an arbitrary choice of a reference where we pick the potential energy to be a certain value. So let's call this, the scale. It's not quite a scale. The absolute values are only able to be introduced by picking an arbitrary reference point. So for example, in the case of our ball that is being kicked here, we know that the work is minus mg delta y, right? So if the work is minus mg delta y, then that means that delta u, capital U, is mg delta y. Now the only way we can give a value u is by picking a reference point. And so we could say, for example, that mg times y plus some constant, and I'm going to call this constant u0, that's our arbitrary reference point. That's the value at the arbitrary reference point. So there's always going to be an arbitrariness in the absolute values of potential energy that is due to the fact that we introduce potential energy only through differences and relate it to physical quantities only through differences. Now, what will we pick as our value for this reference point? I mean, we can of course be we can pick it arbitrarily. So of course we have to be consistent within our choice within a certain problem. But we can pick it arbitrarily. So we'll pick it in a way that helps us, right? So in this case, it might make sense to pick u at y equals 0 to be equal to 0. So in that case, I find that u as a function of y is just m times g times y. So I've introduced an arbitrary reference point. This is my arbitrary reference point, that the potential energy at a height that is at y equals 0 is equal to 0. Or in the case of the picture here, at 0 height, I've introduced through this reference point the fact that the potential energy is 0 in this reference, in this scale. The energy is going to be, potential energy is going to be 0 at 0 height, and then the height is the only thing that will determine the potential energy of the ball. So there is arbitrariness in the potential energy, in the what exactly the scale is, because it only introduces differences starting from the forces. Okay. Nevertheless, even though there's this arbitrariness, it's of course going to be very useful, because I already wrote down that delta U is equal to minus the work, and that's equal to, well, I should have started with a negative sign here. Minus delta U is equal to the work, and that's equal to the change in kinetic energy, delta K. So minus UB minus UA will be equal to KB minus KA. The difference, the negative difference in potential energy is the negative difference in kinetic energy. Or, if we rewrite this, we can just say that UA plus KA is equal to UB plus KB. So I've just taken this one over there, taken the UB over here, and I have the expression that the sum of kinetic energy and potential energy, sum of potential and kinetic energy, is constant. It's the same at point A, it's the same at point B, and of course it's going to be the same at any point A and B in between whatever points you pick, or even elsewhere. So the sum of potential and kinetic energy is constant. Of course, assuming there's only forces playing a role that can be turned into a potential and kinetic energy, and those are conservative forces, because this is also called the conservation of energy law. So this is the law that says the energy, which is the sum of potential and kinetic energy, is conserved or is constant throughout the motion of, for example, this ball. The sum of kinetic and potential energy is going to be constant. So we know, if we turn it around and start from the conservation of energy, if we have a maximum kinetic energy here, we must have a minimum in potential energy. If we go through a maximum in potential energy, we must have a minimum in kinetic energy, and the sum of kinetic and potential energy here will be identical to the sum of kinetic and potential energy at the starting point and at the ending point. So that also tells you that if the potential energy here is the same as the potential, if the potential energy at the start is the same as the potential energy at the end, because, for example, they're at the same height, in particular, that will be the case, then of course the kinetic energy will have to be the same at the start and at the end, at step 1 and step 5. So that's going to be an important expression that we're going to use. This is sum of kinetic and potential energy is constant when we're talking about conservative forces. Of course, that's not going to be the case anymore if we're introducing dissipative forces, because dissipative forces inherently talk about losing energy, about dissipating energy, and about then moving away from this this relationship. Okay, so this was one example for gravitational potential energy. Again, as a reminder, gravitational potential energy is mg times the height plus some reference, arbitrary reference point value. We could pick y to be, you know, there's of course there's a connection, of course, between the arbitrariness of where you pick the origin and y and the arbitrariness of this number here. But in some sense, the arbitrariness in the reference value goes even deeper than just the arbitrariness in picking an axis, because it is an arbitrariness in the energy value itself, which we don't have in the case of kinetic energy, because that is absolutely defined what a kinetic energy of 0 means. There's nothing that can be, you know, there's no doubt about what a kinetic energy of 0 means. It means no velocity. Okay, so let's look at a different example. So this first one was kicking the ball. Football, in this case, we're going to look at a spring. And remember, in the case of springs, the force is minus the spring constant times the displacement from the equilibrium position. So it's one of those restoring forces. It tries to bring the spring back to its equilibrium state, and that's why the force is proportional to the deviation from the equilibrium, and that's why there's a minus sign too, because it brings it back to the equilibrium. So we introduced that to write dw, which is f dx, and so we continued writing that as minus kx dx. We've gone through this derivation before. We integrated this. This is an integral over f dx, or the integral of minus kx dx, which is 1/2 kx squared. Or in other words, the way to think about that is that if you take the derivative of the work, if you take the derivative, then you'll end up with the force, right? Let's see, do I have this right? No, I actually have it wrong. I have a minus sign here. That's missing. Okay. So if we now add some boundaries, so if we do the work from some state A to some state B, then we'll get A to B here, A to B here, and that will be the expression that we have to evaluate between A and B. So if this now has to be equal to minus the change in potential energy, because I know that the spring force is a conservative force, if that has to be equal to the change in potential energy from A to B, or in other words, this is minus UB minus UA, then I know I can satisfy that with U as a function of x is 1/2 kx squared, and again, plus some constant. So my total my potential energy at a position x will be 1/2 kx squared plus some constant. And again, the constant is there because there's always going to be room for a constant, because I only introduced this potential energy through the differences. So what will I pick for my constant? Well, I'll pick, of course, for my constant so that u at 0 is equal to 0. So that constant is equal to 0. But remember, this is a choice. And I have to make this choice if I want to write u as a function of x in indefinite terms without having to always write this constant there. For those of you who know, of course, calculus and who have seen already something more about integrals, you know that in integrals, when you take an integral, there's always this arbitrary constant as well. This is very similar to that arbitrary constant, actually. So So for springs, we'll introduce the potential energy, U of x, that's 1/2 kx squared. Remember also for gravity, I'll write it down again. For gravity, we had that U was mg times y plus a constant. Well, we'll often write this as mgh, where h is the height. So for gravity, as a function of y, we'll have that potential energy is mgy plus some constant. So now we can of course combine that in a setup that includes both gravity and springs, and the total potential energy will be the sum of the individual potential energies. So if we look at this example here, we have a vertical spring that's where there's a mass attached that's moving under gravity. So let's say we start at y equal to 0. We hold this mass there at rest, and maybe the spring is compressed, as it's shown here. So at this point, what will happen if I let go of this mass? There will be two things that happen. If the spring is compressed, it will actually push the mass down. Gravity will also work on the mass. It will pull the mass down. So what will happen is the mass will go down, will go down, will go down. At some point, the mass will reach the lowest point it's going to go. I mean, you know how this works. If you have something hanging from a mass, it will start bouncing around, right? So it will be a point where now the restoring force due to the spring is pulling this mass back up. And it's pulling in just the right magnitude to cancel the downward force of the weight due to gravity on this mass. So we have a point where we have 0 kinetic energy that we start from. At this point, instantaneously, the kinetic energy will be 0 as well. So can we determine at what y value this point C will be? And let's use our conservation of energy for that. So mass on a spring, I guess, is a good name for this. So we have that U at time A, or at point A, plus kinetic energy at point A is U at point C plus kinetic energy at point C. So these are introduced as A, B, and C. We'll come back to B later. So the kinetic energy is 0. This is at rest. This is equal to 0. This is also instantaneously at rest. Or potential energy is U gravitational at A plus U spring at A. Or potential energy at C is U gravitational at C plus U spring at C. So what's going to be our gravitational potential? So this is now where we can actually start using our arbitrary constants to our benefit. What are we going to do? We're going to define our potential energy, or both our gravitational and our spring potential energy, to be 0 at point A. At point A, at y equals 0, I'm going to define this potential energy to be 0 in both cases. I can, because potential energy is only determined up to a constant, so I can pick that constant however I want. The other way to think about that is we can introduce, for potential energy, we can think of y equals 0 here as the reference point where mg times y is going to be 0, so that's convenient. And we can think of this this point also as the reference point for our spring constant. Think of it as maybe this was a spring that was in equilibrium there, and that's where we start from. So now in point C, we have to, of course, express our potential energies in terms of the choice of arbitrary constant that we picked for A. So what will ultimately the expression be here? It's that 0 is, or 0 plus 0 is UC plus 0. So the potential energy at C will have to be 0 as well. Now, what is the potential energy at C? It's going to be the gravitational potential energy, mg times yc, plus the spring kinetic energy, potential energy, excuse me, 1/2 kyc squared. So that has to be equal to 0. So what are the solutions for this? Well, one solution is yc is equal to 0. We already knew that solution. That's the solution in point A. But the other solution is the one that we're interested in. That's when mg is equal to minus 1/2 k times yc, or yc is equal to minus 2 mg over k. So just by using energy conservation and potential energy and picking a convenient reference in our potential energy scale, we can determine that that the position of point C, which is where this mass will come instantaneously to rest, is given in terms of the mass, gravitational acceleration, and the spring constant. So if we go back to the graph, that's going to be our yc, is the distance downward that this mass goes. Okay, I'll put this back up here so you can absorb this. So UA we were able to set to 0. Choice of U gravitational at y equals 0 is equal to 0. And another choice was that U spring at y equals 0 we set to 0. So we could do something very similar, of course, now by introducing, by looking at B. Let's say that B is exactly halfway between A and C. What we can do is calculate what the potential energy is in point B. So we'll know that this is going to be at yc over 2. So we can use that to then calculate the potential energy for both the gravitational and the spring constant. And we could use that, for example, to then calculate what is the kinetic energy that we will need to have at point B, such that UB plus KB, the sum of potential and kinetic energy, is constant and exactly the same as in point A and in point C. So yeah, so someone's asking, where's this y squared gone? Well, one of the y's has cancelled with the yc, and that's the one that gave us a yc is equal to 0 solution. So we had to split that one off. Or in other words, if you want to divide this entire equation by yc, you first have to make sure that yc is not equal to 0. So we have to split our solution into one where yc is equal to 0, and then a path on the right that is for yc not equal to 0. Okay, good. So all of this, we started from the fact that we wanted the forces, and that we can only describe the forces in terms of potential energy when these are conservative forces. So conservative forces are the ones that have a corresponding potential energy, and that's in contrast with the non-conservative forces or the dissipative forces, such as, of course, friction and drag. So conservative forces we introduced as the work is independent of the path, right? That's how we defined conservative forces. So if we write down the work for a path AB, for one path, path 1, that will be the integral from A to B along path 1 of F dr, right? We can write this down for path 2 as well. The work from A to B along path 2 is going to be the integral from A to B along path 2 of F dr. So that's going to be my point A. This is going to be my point B. I have my path A, path 1. And I have my path 2. This is path 2. In both of those cases, this has to be the same value because the work only depends on the initial point and the final point. It doesn't depend on any of the details of the path in between. So what does that mean? I'll need some more space here. That means that if we now create an integral that goes along the closed path, that is, well, let's do it in the other direction, that is starting along path 1 and then coming back along path 2, along that closed path, and I'm going to indicate that this is a closed path by drawing a little circle on the integral here. It's a closed path, that's why I can draw the little circle there. F dr, the integral along this path, will have to be 0 because it is the integral, the work along path 1 minus the work along path 2. So, of course, that means that no work is done by conservative forces along a closed path. And that's, of course, what it means to have energy conservation, that if you go in a circle or in any closed path, that you don't lose any energy, or in other words, that no work is being done and you're exactly where you started from. So when will this be true? Let's try to write something down that is a property of the forces. So this will be true if F dr is something you can write as the total derivative of something. If you can write this as a total derivative of something, then the integral of this total derivative just becomes the difference of whatever is in here in the parentheses, and if you go over a closed path, you're essentially subtracting it from itself, and so the integral becomes trivial and becomes 0. So this will have to be true, and we know one case in which this is true. That's when we wrote this as d of 1/2 mv dot v, right? And then we did the derivative, and that's where I gave the little side note about physicists doing weird things with calculus sometimes. But that was one of the cases where the work, this is the infinitesimal amount of work, is a total derivative of the kinetic energy. Now, when will this be true? And this is what we write as, this is, for example, fx times dx plus fy times dy. This will be true when a condition is satisfied, and I'm going to refer to, not to Carl, to calculus. This is true when the derivative of fx to y is equal to the derivative of Fy to x. So if this is true, then we have a conservative force. We can check that this is true, right? We can check that this is true for example, gravity. Fx is 0, Fy is minus m times g. So dfx dy is equal to 0 because fx doesn't depend on y at all. And dfy dx is 0 because Fy doesn't depend on x. So this will be a conservative force. And this will be a fundamental property of conservative forces. That is a way to check whether a force is a conservative force. And you'll see that that doesn't apply to friction. And with that, that's it for today. So thank you for staying here 2 minutes later. And we will talk again on Wednesday.